So to run simple linear regression, you'll just go ahead and launch your SPSS software, open up your data set, you go to the Analyze button, which will give you a drop-down menu. You'll move down to the Regression tab, which will give you a sidebar menu. Then you just go ahead and click on Linear. So for this first example, we're going to go ahead and move the variable, our dependent variable v2 into the dependent box, and then we'll move variable v4 into the independent box. We're going to go ahead and click on the Options tab, and we're going to go ahead and check to make sure that we've got the estimates selected, confidence intervals at 95%, the model fit, and the R-squared change. From this point, we'll go ahead and click on Continue and then on OK, which of course will give us the SPSS output. And for those of you who have been using SPSS, you realize there's a number of tables that come out and text that come out of the output. I'm going to focus on just the model summary and the coefficients tables for this presentation. So the model summary, we actually have the R and the R-squared. And for here, let's just focus on the R-squared. The R-squared gives us, in essence, the percentage or an idea of the model fit. The R-squared value here is 0.977, which translates to being almost, it lets us know that approximately 98% of the variability of the data can be explained by the model. So that's fairly high. The next box that we have is the coefficients table. And we can see that we only have one model because this is simple linear regression. We can see the value for our constant, which goes to the right under the large B, which is 0.011. And then we can see that our independent variable, V4, the unstandardized coefficient, which is the large B, is 0.996. There's also a standardized coefficient, but for simple linear regression, I recommend that you just focus on the unstandardized coefficient, which is the large B. We have our column which has our sig value. Actually, I'll just back up one. There's the t value, which is 204.7, and that's used to calculate whether or not the value, the unstandardized coefficient, is significant or not. And we can see that in the significance column, which is equal to our p-value, it's 0.000, which means that it's less than 0.005. So this is a significant coefficient for our mathematical model. And then we have the 95% confidence interval for our coefficient, which ranges from 0.986 to 1.005. It's important to note that the confidence interval for the large B does not include the value of 0. If it includes the value of 0, then we know that the slope of the line may be 0, and so there is no linear relationship between the independent variable and the dependent variable. Moving on, if we wanted to see what this looked like in terms of a scatter plot, here we have it. You can see that there's a number of points, and you could pretty much draw a straight line at about a 45-degree angle, or in this case, this matches our coefficient, which is very close to 1. For our next example, we'll go back to our same data set, but this time we're going to use the dependent variable is going to be variable number 5, and our independent variable is going to be variable number 8. We'll go ahead and replace those values, keep everything the same, run the analysis, and when we look at the model summary, we can see that our R-squared value is 0.947, so just about 95% of the variability is explained by the model. Then moving on to the coefficients table, we can see that for variable number 8, the unstandardized coefficient, the large B, is actually negative 1.00. So we're going to have a negative correlation. And we can see under the sig value that it's 0.00, which is significant. It's less than 0.05. And our confidence interval does not include the value of 0, so that's all good. And when we look at our scatter plot, you can see this is a slope, a negative slope. So it's the coefficient was negative 1.00, and we can see this that as the independent variable increases, there is a decrease in the value of the dependent variable. So this is a negative slope here. For our next example, we're going to go back to SPSS. We'll change out the variables again. This time, for the dependent variable, we're using V12. And for our independent variable, we're using V14. We'll keep all other selections the same. We'll click on the OK button. In our model summary, where we have V12 and V14, we can see that our R-squared is quite a bit different than our previous examples. Our R-squared value is 0.003. So if we were to write this up in APA, we would say that less than 1% of the variability is explained by the model. So at this point, you should somewhat recognize that this model probably isn't that good because it's explaining less than 1% of the variability. And we look at our next table for coefficients. And if we look at the coefficient for the independent variable V14, the unstandardized coefficient, the large B, we see that it's 0.112. So imagine this is rather flat. The previous examples, the value was much closer to 1, and we saw that in our lines, even if it's 1 or negative 1. When we take a look at our sig value is 0.085, which is greater than 0.05. So this is statistically not significant. And if we look at our population estimate, which is the 95% confidence interval, we see that it ranges from negative 0.016 to 0.240. So here we have the confidence interval which happens to span across the value of 0, which relates back to why this is not a significant result. I'm sorry, this model is not statistically significant. And when we look at our scatter plot, we can actually see why this is not statistically significant, why the model was not so good. It's really difficult to plot a line through all of this, which would represent the data points. So for these next examples, I'm going to step away a bit from the linear relationship, and we'll look a bit more at the meanings of the R-squared, the variability in the data. So we're going to go ahead and change out our variables again, and we're going to be using, for our dependent variable, variable 8, and for the independent variable, it'll be variable V10. We're going to go ahead and keep everything the same and click the OK button. In our model summary, we can see that the R-squared value now is 1.00. So what this is telling us is that our mathematical model is explaining 100% of the variability in this for our data. And for our coefficients table, for variable V10, we can see that the unstandardized coefficient, the large B, is actually negative 0.350, meaning that we're going to have a negative line here. And because it explains 100% of the variability, SPSS is not actually able to calculate the sig value because it's actually a perfect relationship. We can even see that with our 95% confidence interval, that the confidence interval actually doesn't really span any range. It's just a point estimate of negative 0.350 to negative 0.350. And when we do our scatter plot for variables 8 and 10, we can see it right here. So we've got a negative slope, which is 0.350, and our mathematical model explains 100% of the variability. And so this is where you can see how tight well, essentially there's just a straight line of the data points. Now, if we go back and we switch out our variables again from the data set, and this time we're going to use variable 3 and variable 5, we put those in, we click the OK button. our model summary, when we focus on the R-squared, we see that it's 0.944, which is a little more than 94% of the variability. And then under our coefficients table, for the independent variable V5, the unstandardized coefficient, the large B, is also the same. It's 0.994, very close to 1. We see our sig value is statistically significant. We can look at the confidence interval ranging from 0.930 to 0.958. So it's a pretty tight confidence interval. We know that's statistically significant. And then here we see that this is where the model, the R-squared value, actually explains 94% of the variability. You can see that the data points are scattered out a little bit, but they're still pretty much in a line, and you can just see how much different this is from the previous example where we had 100% variability explained, which gave us a straight line. So for another example, we'll go back to SPSS, and then we change out our variables to, this time we're going to run variable 6 and variable 13. We'll click the OK button. Our model summary, and this time our R-squared value is a bit lower. It's 0.006. So it's explaining less than 1% of the variability in the data. For the independent variable V13, our standardized coefficient is 0.030, which is very close to 0 in itself, but however, we can also see that even though the coefficient is very low, it is statistically significant because the sig value is 0.015. And then when we look at our confidence interval, just to check it, we can see that the unstandardized coefficient, the 95% confidence interval, ranges from 0.006 to 0.055. And then on our scatter plot, we have this, which is very similar to what we saw earlier. However, SPSS was able to use our data and actually calculate out a mathematical formulation for this data point in a simple linear regression. So when you look at the scatter plots of your data, if you're fortunate, you'll see a very tight group, which you can pretty much imagine a line describing that group, or you may have something where there's very low explanation of the variability, and you'll have something similar to what you're seeing here. However, SPSS was actually able to calculate out a mathematical model which was statistically significant.